So I want to talk about some of the features of waves. One thing you should remember is that a wave is a disturbance in a medium, or just a fluctuation, that might take on a form that looks something like this. And if we're looking at a waveform that looks something like this, there are a few characteristics that we need to think about, because the terminology comes up over and over and over again. One thing that we think about when we talk about waves is called the amplitude, A for amplitude. And really, that's how much a medium has been disturbed from its initial rest position. Another thing that we might talk about is a wavelength. And when we're talking about a wavelength, we're talking about the actual physical distance it is from one point on a wave to the next identical point in a wave cycle. Like physically, the distance from one spot to another spot that's exactly the same on a wave cycle. And so maybe you look at this and you think of this as kind of like a cosine wave, and you go from the peak to the trough, back up to the peak again. That's one whole wave. We could have also gone from this point here to this point here, because notice that that's from the beginning of a wave all the way back to the point where you start to repeat the waveform again. So we call this a wavelength, and it's represented by the variable lambda. So lambda, the Greek letter lambda, typically represents wavelength. Oh, I should say for amplitude, we could have measured the disturbance as a negative amplitude, and both of those A values should be the same. Both of them are amplitude. Another thing that we think about when we talk about, let's just call it the anatomy of a wave, is the direction of wave travel. And waves actually travel. And you can think about waves on a pond, or when you're having a bath in the bathtub, or in the backyard, wading around in the kiddie pool maybe. Direction of wave travel might be talking about ripples, or it might be talking about continuous waves traveling across a swimming pool, for example. Another thing, if we go back to amplitudes, is we could talk about this positive amplitude as being measured at the point where there might be a peak, and a negative amplitude measured at a point where there's a trough. A lot of different variables here. Oh, I did forget to talk about the rest position of the medium being disturbed to produce the wave. There are a few different types of waves, and actually this is kind of an illustration of the first type, a transverse wave. And a transverse wave is a wave where the medium is disturbed so that the actual particles that make up the medium move in a way that they go perpendicular to the direction of wave travel. So if we have a direction of wave travel that's this way, a transverse wave is that type of wave where the particles actually wiggle back and forth, even though the wave is traveling maybe left to right in this diagram. Each individual piece of the wave, each particle of the wave, goes back and forth. And a lot of times people talk about, like holding onto a slinky. This is a mitten holding onto a slinky, and the slinky gets wiggled back and forth by a hand that goes up and down. And you can imagine taking a great big slinky, or I remember when we were kids, the children out in the schoolyard used to do this with a skipping rope, and they called it sneaky snake, and you had to dance back and forth across the skipping rope, but you wiggled your hand back and forth perpendicular to the direction that you actually wanted to send wave pulses along that snake or that spring or whatever it is that you're trying to disturb. That's a transverse wave. A classic example of that is a water wave. The actual individual water molecules move up and down, but the wave itself propagates, forward. This is a nice example of the water wave. And while we're talking about water waves, let's go back and label this up. I want to make sure that everybody can see that this would be where the peak is, this would be a trough, amplitude, and you do have a repetition of waveform. So from here to here, we have one wavelength. Or, like we said before in terms of cos waves, I could extend this up just a little bit more. And if there's another peak, from peak to peak is one wavelength. Or I could say, hey, from trough to trough is one wavelength. From one point to another identical point is one wavelength. So that's a transverse wave. I want to take this away for a second because the other major type of waveform people talk about is a longitudinal wave. And a longitudinal wave is one where, let me draw this first. Oh, maybe I'll describe it first. No. I've decided. I'm going to draw it. Let's draw a mitten again. And this little mitten hand has got, let's choose a big spring again, like a slinky. And would you believe it, if I wiggle my hand, not up and down like we did before, but pull it back and punch it forward, I can actually make density packets. And I tried my best to make it look that like these guys here are closer together and these guys here are further apart. We could punch this spring back and forth, back and forth, back and forth, and you could make dense regions and low density regions. And the high density regions we call, maybe even logically you might figure this yourself, compression regions. Compressions. And the low density regions, this is maybe a word that might not come up so much in regular conversation, rarefactions. Please don't mix this up with refraction or some other word that you might have come across previously in your life. It's not the same word. Rarefaction talks about a rarefication of wave particles. They're spreading out. If something's more rare, then those things are fewer and further between. And the same thing is true in a rarefied region of a wave medium. If you've produced a rarefaction, you've spread out the particles. In a compression, they're exactly what it sounds like. They're compressed together. Don't mix this word up with something that you might have heard before. Rarefaction is what it's called. And so we might define a longitudinal wave as a wave where the medium is disturbed so that particles move. Some people say parallel. I want to say collinearly. With the direction of wave travel. And all I mean by that is that I'm going to punch that spring back and forth, and while the waves or the density packets might travel this way, and instead of saying direction of wave travel in this label, I'm going to just say that it's a velocity for the wave. The wave's got a velocity, and that velocity is in the direction of wave travel. That wave is going to travel as successive repeating pulses through space, and the successive repeating pulses traveling through space are going to be back and forth in line with the hand that was creating the compression and rarefaction regions. Alright, so I've got this wave vector, if you like, traveling through space now. I've got compression regions, rarefaction regions. Now, how do you measure a wavelength on such a thing? Well, it goes back to what a wavelength is. A wavelength is the measure of the distance between identical regions. So even though this doesn't look like the good old-fashioned wave that you're used to and you grew up with and mom and dad told you stories about when you were a kid, the definition still holds up. That's a compression region, and that's a compression region, and from the center of one compression region to the center of the next compression region is a wavelength. That's lambda. From the center of a rarefaction region to the center of the next rarefaction region is also lambda. You know, people sometimes are unsettled by something like this being called a wave, but you shouldn't. It fits the definition, right? In fact, if you really want to force the issue, you can take a wave like this and say, hey, you know what, I don't like the way that looks. I'm just not used to this whole longitudinal wave thing. Why don't we graph the whole darn thing? Why don't we graph it as a graph of, I don't know, density, particle density, and I don't know, distance or position. So if we graph it as a function of density versus position, you'll find that it goes from a high dense region to a low dense region to a high dense region to a low dense region, and it's gonna follow the same pattern. And the distance between this position and this position is the same sort of distance that we mapped out up here, high density to high density. It's still lambda from one position to the next. It's just that this looks like the traditional good old-fashioned transverse wave that you grew up with, but this is no less a wave. We've defined it as a wave. Beautiful. Makes me feel good inside. All right, time for a quiz. If I've got something that looks like this, something that looks like this, I'm going to label up a few things here. I want to label this measurement B. I want to measure from here to here. Let's say that we could measure that and call it A. I want to measure from, let's see, from here to here, and I want to call this E. And from, let's see, here to here, let's call that one C. And how about from here to here, we call that D. All right, so we've got this thing all mapped out. I want to ask a few questions here. Which one of these is the ... amplitude? I'm not going to answer it. Answer it in your head. Which one of these is the wavelength? A and lambda. And which one of these is the half wavelength? And by the way, since half wavelength shows up so frequently, it's actually a really important thing in waves. You know, we'll come back to it over and over again. People will actually write lambda over 2 instead of the word half wavelength sometimes, because it's so common. By the way, they do the same thing for quarter wavelength, because quarter wavelength is a real important thing too. But I don't want to get into that just now. Anyway, let's go back and look at the answers to these questions, because I'm pretty sure that most of you have answered it in your heads already. The amplitude, of course, is D. The wavelength can be measured by A. And I mean the measurement A, not A for amplitude. And the half wavelength, lambda over 2, can be measured by, now this is a bit of a trick question, some of you probably said C, and some of you said E, and the clever ones said both. They're both a measure of half wavelength, because it's half of the length of A, and I could actually measure this out. Look at this. I take this A measurement, I compare it to that measurement for C. The A measurement is going to be twice as big as C if I've drawn this correctly, and the same thing for E. E is going to be half as big as A. Yeah, I think we're sold on that one. Alright everybody, that's the basic anatomy of waves, and that's where I'm going to stop.